So thank you all for joining today's webinar, Beyond Optical Metrology. We're really going to dive into challenges for traditional optical metrology systems and how GelSight can help with those applications. So I'm Abby Lindberg. I lead GelSight's applications engineering team. And with us today, we'll have Alejandro answering questions throughout live on the Q&A. So feel free to use the Q&A chat. You might have to click more at the top of Teams to get to it. And then we should have a few minutes for questions at the end as well. Just a reminder, we'll be posting this to YouTube after the session. And with us today, we have Dennis Lang. So I'll hand it over to him to introduce himself and give us some background about these types of applications.
Yeah, thanks, Abby. And I appreciate everybody's time here today. I'm Dennis Lang, Chief Business Officer here at GelSight. And just want to kind of set the stage for what we're going to be talking about today. And really that is some of the problems or challenges given by certain tools that exist in the industry today and are in regular use, of course. And many of these critical inspections rely on legacy methods or optical sensors that were never really designed for real-world surfaces. The shiny metals that we see in many of these assemblies, as we see here on the intro slide, cause glare. Transparent parts confuse depth. Darker composite materials lose contrast, and corrosion or coatings make dropouts that compromise data quality and also take quite a long time in reconstruction. The result is inconsistent measurements, subjective calls, and inspection gaps, especially in production and field environments. GelSight, with our tactile sensing platform, takes a fundamentally different approach. We use a 3D sensing technology that directly measures surfaces through controlled contact rather than through reflected light. And this leads to many advantages we'll talk about today for certain scenarios. Not any one tool is the perfect one for every situation. But GelSight, by using our compliant gel, has an engineered optical path that controls the contrast at the surface and defines the depth of the field exactly where the measurement occurs. This is why we're able to do a mobile measurement, just like you see here in this slide, without having to fixture the system. A little bit of handshake or a little bit of angle, our system can handle that. It's designed around that, as opposed to many of the optical solutions that are on the market. And this allows, of course, for a mobile solution that can work at the point of need. We do many different applications because of this at GelSight. It's a lot of fun sometimes to really see what comes in. But aerospace really has been kind of our historical bread and butter with energy and forensics. But some of the applications we see that are really interesting, aircraft transparencies. We have a really unique ability to measure aircraft transparencies, whether that's on commercial jetliners or on fighter jets. We look at coatings, we look at pitting, coatings that can peel off. We've been called in for all kinds of different measurements like this, both for new production buy-off and for MRO and sustainment type activities. Corrosion and pitting are big ones for us. Highly reflective metals, obviously, again, composites, bonded composite to metal structures. So we'll be showing composite structures later, both blended, in that case, glass and metal, but also we'll be showing some composites. Coatings, and again, that blended demo we'll have today will be on a smartphone. That'll show you that. So I'll pass it back to Abby to show you some of the different things we can inspect and encourage people to think about and even start asking questions about how some of these inspection gaps could be closed by what GelSight has to offer.
Thanks, Dennis. So I'll start with a little bit of a overview of how GelSight works, kind of highlight some of the reasons why we can handle those materials that Dennis was just talking about. So I have our Series 2 system here. We'll also use our Modulus system today for the applications we'll review. But we've got a camera and a lens and an illumination system in here. And I'll take the gel off of the top so you can see inside. And we've got 6 banks of LEDs. And when we click this button, we're taking 6 images, one with each one of those LED banks illuminated. And that works in conjunction with our gel sensor. And this is really what enables us to look at any of those materials, regardless of their optical properties. So regardless of the system, each one of our gels consists of an acrylic base, and then we have a layer of gel here, and then a pigment layer. I'll hold up the other form factors we have. So we've got our max gel here, just a larger form factor, but you'll see pretty much the same on the end here. We've got a gel and we've got a pigment layer. And same for the modulus system too. I'll hold this little one up here. So we've got the gel with the pigment on it. And that pigment is really, going to enable those transitions between materials, those transparent materials. So we don't actually care what it looks like because we're looking through the other side of that layer. So no effects of ambient lighting. We don't care about that. We could look at something backlit and that would be fine too. Reflective, fabrics, anything. It's all going to look the same to us. So hopefully you'll see some of that as we go through these demos here. So I'm going to put this back in and I'll go ahead and share my screen. And as I do that, I'll have my video going, but I'll also have the screen share going. So to make one kind of the main view, go ahead and click between them. If you want to see the video larger, click on the video. If you want to see the screen share larger, click on the screen share. Just a little team nuance there. So let me go ahead and share our software. We'll click go live, and I'll also change my video view here so that we can see my tabletop. All right, here we go. So the first thing that I'll do is actually one of our favorite things to do in a demo to make this kind of real is to stick our finger on the end of it here so you can see my fingerprint. So I'm just pressing my finger into the end of this gel here just to give you an idea of the sensitivity or resolution. You can see the pores on my fingerprint here. So I've got a few different applications that we'll go over today. And the first one, is going to be transparent materials. Dennis was talking about this being a big application for us. This is a typically pretty challenging application because of the material, but also accessibility. So we'll talk a little bit about that. I have a window here from an airplane, and we've got a few defects on it here that I'll scan, and we'll take a look at those. So I've got our software open. And I'll actually start this a little bit differently. I'm going to run our defect detection algorithm, and it's going to output the characteristics of the deepest defect that we find in the field of view of the system. So I'm going to run that, but I'm going to run it in an automated way. So we call this running a routine. I'm going to check this box in the software here, and I have defect detection selected. And if I mouse over it, you can see automatically measures these characteristics of the deepest defect in that surface. So I'll just go ahead and take some scans of these defects. You'll see them live on the screen as I find them. We can take a look at that one. I'll move over. Maybe we'll take a look at this other one here. It looks pretty similar, but it's actually a different defect. Maybe we'll look at a different one with another form factor as well. Something like this one here. So I just went through and took 3 different scans with our Series 2 system and automatically characterize those defects. And I'll open them up so you can see what that looks like. We'll take a look at this surface. This is the first one in 3D. And some of you that might be familiar with GelSight already have seen this view if you've upgraded to 4.3. So this is our new rendering engine just launched in 4.3. I think it looks great. You get a lot of resolution on these defects. Zoom in a little bit on that one here. And I'll jump over to analyze so we can see the result that came out of our defect detection analysis. We can see the characteristics of that defect, the profile through the deepest point, and then of course we can turn that directly into our PDF report and customize that as needed. There we go. I'll go ahead and open up a couple of those other ones here too, so we can see how they compared. Here's that second one, same type of analysis. And we'll go look at this third one as well that had a different, this was more of a scratch as opposed to a dent. We can see the profile through that here. So I'll jump back over to the capture page. I kind of briefly mentioned accessibility. So obviously the transparent material can be a challenge, especially if there's a coating or a film over any of these layers. The question of are you measuring the film or are you measuring the surface underneath it can be a challenge for different optical systems. But the other thing that can be a challenge is this might not be, in this example, it's on my desk, right? But in in other scenarios, it might be on, installed in the fuselage. So I'll actually change my video angle here. And some of you that might have joined a webinar in the past see that I usually sit next to this in the back here. And we'll actually go and take a scan of the defect on this window that's installed in this, as opposed to the one on the desk, to kind of show the portability of the system. So I'll just kind of roll back over here. And here's this much larger defect. And I just click the button to take the scan. And we'll go open that one up in just a second here. All right. So I'll run our defect detection analysis on our field of view here. And we can see the characteristics through that deepest point. Same as the other one, same default settings, different defect, no settings changes. And I'll open up the 3D for this one too, because this one's pretty crazy looking. You can increase the scaling or decrease the scaling, but this is, I think this looks great with our new 3D rendering engine, the 4.31. So if you're seeing this for the first time, I think hopefully you like it and want to get that new install. All right, so the next example that I have here is going to be, as Dennis mentioned before, we've got a smartphone example, and this will be, difference looking at transitions between materials. So I'll go ahead and share my desktop again so we can see that. We'll switch over. And we'll look at a couple different scans on this. We'll look at a couple different surfaces on this. We'll look at the profile, across the edge here, where we transition between the glass and the metal on the side here. And we'll also take a look at the logo. It's got a very highly reflective material where the logo is compared to the matte laser etched background. So I'll go ahead and take a scan, and we'll start with the logo first. We can see that little leaf. It's a little bit hard to see, but we'll go look at this scan afterward. I'll actually turn off defect detection so that we're not looking for a defect on this. But I will open this scan up and we can see the 3D here. So I think that, enhancing this, scaling it up a little bit to see some of the smaller features better. It's pretty nice on this. You really see the difference between that textured surface and the very highly polished surface. But we're not seeing any kind of data dropouts. Once again, no settings changes between the two different, highly different reflectivities here. So I'll jump back over here. And I'm going to zoom in so we can see, the top of that leaf pretty well, and maybe we'll just measure the height of it. So I'll use our offset analysis function here, and we'll just draw a line, across that transition. And I'm going to do multiple profiles for this to average them. We'll click Analyze, and I'm going to add a reference surface as well. So I'm going to say where my 0 is. We'll pick down here, and maybe I want to compare the average of that upper surface to the average of the lower surface and measure that step height at this specific interface. We're getting just on about 4 micron for that step height here. Now the other area on this with the transition that we'll take a look at, we'll look at the profile along the edge here. So I will take another scan of that. We'll look at that interface. You can see I actually have a little tiny scratch on my phone there. But that's going to be the transition between this edge and this material. You also see as the backlight changes, there's no difference to the Gelsite scan if the light is on the phone or not. So I think that's kind of interesting to see. I'll open this up. We can see this in 3D as well. We'll decrease the scaling to make it look 100% here. And that's what that interface looks like. Once again, no kind of data dropouts from that missing from any kind of that transition between those materials. And we could take a look at the profile between these materials. Just draw a line like that. and add our reference surface again at maybe this flat part of the phone here. And whether the interest would be in, maybe we care about the radius at the bottom of this, maybe we actually are caring about the difference in height between this interface and this one here. We have some options for different measurement analysis tools in these cases. Now I have one other example that highlights the transitions between materials. So I'll go back to capture here and I'll take that sample out. And this sample that I have is not necessarily representative of what most of our applications are in composites, but I do have part of a hockey stick here. So maybe as I take this scan, maybe Dennis, could you talk a little bit more about carbon fiber applications that we have in the field?
Yeah, sure. And of course, if anybody out there wants to donate a carbon fiber part to us, we'd be happy to use it in the next webinar. But yeah, talking about the composite structure here, we drilled a hole in a hockey stick to show what a hole within a carbon fiber structure looks like and why Gelsite might offer something unique here. There's a couple of things to see. That damage on the surface to the bottom right is the drill bit actually walking across. I happened to do this drilling, so I know that was me. But then once the bit dug in and drilled the hole, you can see a couple of different things that are very typical of composite holes, even in highly sensitive areas and applications. And that is you start to see chipping around the edge where you either have some delamination between the fibers and the resin. You can chip that resin at the surface. It's often a very brittle material or somewhat brittle material. Then it fractures like that. What Gelsite really offers is the ability to measure that hole, like Abby is showing you here, without any distortion. So many techniques that are used in environments to measure carbon fiber holes can actually distort the hole or even damage the hole. We're able to very quickly make that measurement, as Abby showed. Within the hole, you can start to see layers of the material. And if you're thinking of like an aircraft fuselage, you could see if you're drilling damaged the ESD mat, for example, that's in there for protection to electrical energy for the aircraft sensitive systems, of course. You're able to see if things are delaminating. You're able to make a study of, is something going on at these drillings that's leading to paint not adhering properly and peeling off in the field. So there's a lot of different things that Gelsite can offer in one scan that bring a lot of value, whether or not you use a hockey stick to demonstrate it. So.
Yeah, exactly. So kind of another thing to point out here, which you touched on when we talked about different materials. This is obviously very different materials between the layers that we're seeing, and with other optical systems, this might require multiple light settings, multiple light levels, and scan stitching to get that kind of data on the surface to minimize those data dropouts, which can be, it can be a lot of time, especially with the having to take scans of the same place over and over with different light settings. So I've got one more example here that we'll look at with series 2. And this is another one that's challenging for the same reasons and also other reasons for optical systems. And I'll take basically any kind of abrasive material. I'll go back to capture here and we'll take a scan of it and we'll talk about why. But I'll come in here and I'll just take a scan of this surface. And this can be challenging because of the same transitions between materials. Again, your abrasive material, your adhesive, your coatings might all have different reflectivities and can be hard to see. So really with Gelsite, you can see that kind of crystal structure out of that. And whether this means you want to measure the size distribution of these particles, maybe with our particle detection algorithm here, or maybe it's the roughness of the surface that you're interested in. We could do surface roughness or profile roughness on this. I'll just do surface roughness as an example, just to quickly get our average roughness over area or other S parameters as well. So just a quick output for average roughness here. And so this can be challenging because of the different materials, but also the geometry of those particles. Sometimes these rougher surfaces, these are actually going to be a lot more challenging for these optical systems because of the numerical aperture required for the resolution to get to these, but then that also limits the angles that you can measure on the side of these. So the kind of structure of these having steep angles can be typically challenging for some of these optical systems too. And with needing a larger field of view to measure rougher surfaces is also part of the ISO standard for roughness measurements. So that larger field of view with the higher magnification is just a lot of time in general, time and challenges. So I have one other example that we will go over. We'll switch gears over to looking at the modulus system. I've got this copper pipe fitting here to kind of talk about reflective materials and also just accessibility challenges. So I'll actually unplug, go to capture here, and we'll disconnect our Series 2, and we'll just connect our modulus system here with the 90-degree attachment. Let me move that one out of the way. I've got this one here. Lights on, we're ready to take some scans. But we've got a copper pipe fitting here, and it's got a defect on the inside, and this diameter is a 1-inch diameter, just for some scale reference. So I've got a defect in here that I'll take a look at. And I'm just going to take our system here with the 90-degree attachment and go into the edge here. And we can see that little defect right there. And I'll just take that scan. So, same challenges that we've been talking about with reflectivity, but also just accessibility. I mean, this is something that would typically involve replica material to measure it. You're going to have to set up your replica material and then bring it to a lab and measure it that way. Would be kind of the most common way to measure this. So really just being able to do that in situ to get to these locations, I mean, is a big benefit for this application. So we could come in here, we can look at this in 3D as well. You can see the curvature of that pipe there. And let's use our defect detection algorithm on this too with the same default settings. We'll look for a defect in that area, and we can see the output. Since this is our latest software release, I'll also mention that defect detection has now expanded its use cases to curved surfaces as well. So we're looking at using defect detection on cylinders. It's a good fit for the analysis function now. So the last thing that I wanted to share is a little bit of a fun one. I'm not going to do it live, and you'll see why in just a second here. But we've had a bunch of snow in New England. We're in Massachusetts here, and this past weekend I was able to catch some pretty cool pictures of some snowflakes. So I figured, this is definitely an optically challenging and needs to be done. Probably melt if you're trying to bring them to a lab, right? So I was outside doing this. But I'll just kind of click through a couple of these because they have different, every snowflake's different, right? So you've got the different crystal structures across these, and they're just kind of a fun one here. There's another one here. I got half of one in this one. And then the last one I'll show, this one's probably my favorite. As you can see, a lot of the snow that's coming down looks like these little clumps of, bits of snowflakes. And then I caught the full snowflake on the side there. So just kind of a fun one with challenging optics, but might not be a little bit out of the box here. So maybe I'll hand it back to Dennis to talk about the value brought by GelSight for these types of applications to kind of summarize that.
Yeah, thanks, Abby. And I see there's some questions, so I'll make this brief and we'll get into those. But really the right way to think about GelSight is we created a tactile sensing platform, which offered many different capabilities within the industry, including things outside of metrology, like robotics. But we have the purpose-built for metrology, max, modulus, and mobile solutions that we've had on the market for many years now, which bring fast and easy 2D and 3D measurements to pretty much any environment you would need to take them. When you see something like defect detection, especially when you start running it as a routine, you get to very quick pass-fail decisions, which are extremely useful. We are today doing everything. We started in the lab with benchtop systems. We got into kind of production and new production with our mobile. And as we've hardened those systems, we've gotten to sustainment, MRO, and even field locations where we're making readiness decisions. We have situations where people are on the jet, decisions are made go, no go with GelSight today, which is great. The other thing that's really interesting when you think about GelSight is your future proofing. So GelSight creates computer vision based data. Those that are part of our ecosystem and have our software now, we release 3 updates and upgrades a year typically. And every time we do that, all of your GelSight scans can be used in the new software. So you can apply as the latest advancements in computer vision analysis come out, they can be retroactively applied. This helps not only within the GelSight domain, but you're able to take these results into some of the proprietary models our customers have for quality, for strength, for fatigue modeling, all these different kinds of things. And ultimately, this is going to lead to AI-driven sustainment, which will really be a great thing. Finally, and maybe one of the most important things, a lot of these problems in the industry are solved with different tools. But what GelSight offers is anything from the lab to the field can be done with GelSight, giving a continuity in measurements. We have many customers talk about how they're able to much more efficiently communicate through a material review board meeting or a quality review meeting because of the data they bring with GelSight. So we appreciate your time today. And I'll let Abby wrap it up and get us to questions.
All right, awesome. Thanks, Dennis. So it looks like we have several questions in the queue here, so I'll kind of go through. It looks like some of them Alejandro published already, so I'll kind of run through those as well. What is the pressure you need to apply? Great question. It does depend on what you're measuring. So if you're measuring something, kind of hold this up again. If you're measuring something pretty flat, you just really need to make contact with what you're measuring. So if you imagine something flat, you barely have to push before the whole gel surface is going to make contact. If you're measuring something like a deeper groove, you're going to have to press down harder. I would say it's a force that you can apply with a single hand. I don't have a number to give you for that because it does depend on what you're measuring. But when I showed my fingerprint being scanned in the display, I was basically just pressing down like this, nothing kind of crazy. Dennis,
Single digit pounds of pressure is the way to think about it. We actually have an app note for those. Just reach out to us and we can share actually accuracy versus pressure. Abby's team has done this before.
Yeah. What is the maximum depth that GelSight can measure? Is it limited to the height depth of the gel itself? Okay, so Alejandro already answered this one. Typically about 1 millimeter. It does depend on the geometry of the surface, but about 1 millimeter, and all of our accuracy studies include 1 millimeter reference standards as well. Is it possible to get a measurement result directly instead of having to open each file manually? Yes, depends how you want to configure that. I did just show running a routine. I didn't have any pass-fail criteria in there, so everything was green, but you could configure this with your own pass-fail criteria. You get a pass or a fail when you take the scans. We also can export CSV files or bulk export those PDF files without having to open them individually. We do also have an API for integration. So if you want all of this data to go in an automated way to your system, you're on your network, great. Go ahead and automatically send that using that API. So. All right, let's see other ones we've got in the queue here. Probably time for just 1 or 2 more. For surface profile measurements, can you change cutoff filters and other parameters to be in line with ASTM or other standard specifications? Yes, so we can configure the filter cutoff, and our user manual will actually go through the ISO and ASTM standards that each parameter that we output is supporting. So we are following those standards for those calculations as well. If you have questions about a specific one, definitely reach out, or we'll probably reach out after this as well. Must the sensor cylinder be hardwired to the laptop computer, or is there a wireless option? Dennis, you can answer this one.
Yeah, there's a couple of things to say about this. So we use USB-C for both data and power. And can GelSight be made wireless? Yeah, that's actually pretty straightforward task. The reason it's not wireless today is based on our customer base, not technology. What I mean when I say that is we're in many sensitive environments where there is an explicit need not to broadcast wireless signals from the system. So we have stayed wired for that reason. But yeah, putting a battery and wireless antenna on the system is no problem. Maybe someday we'll do that, but so far, the engineering efforts have gone into some of the things our customers need more, like the modular system with access and new lenses which are coming and things like that.
All right, I think it looks like we're at time here. We have a couple other questions in the queue, so we'll make sure that we'll follow up after this to answer those. But thank you all for joining today. And reminder that this will go up on YouTube afterward if you want to watch it again. So, all right. Thank
Thanks,
you.
everybody.